so it's like 2 times is 2 plus 6 is 8, right? And 2 times 3 is 6, plus 2 times 3 is 6, is 12, and 2 times 4 is 8, plus 15 sounds like maybe 23, and 2 times 7 is 14, plus 12 is maybe 24. Is that what you guys? Excuse me, I did my arithmetic wrong?
26 maybe.
Oh, yeah, because it's going to be 12 plus 14 is 26, right? Okay. Okay. So that's and there's some, you can also subtract matrices, but that's just adding the negative. It's just going to be, if B minus A is going to be Bij minus Aij in terms of the entry. So it's just a natural extension of addition. And there's some examples here. Okay. Now, according to those definitions, there's various properties of this arithmetic. So, for example, and these are useful they're sort of like, to some extent, the matrices obey the same properties as numbers, but not quite all of them. The additive properties are almost completely analogous. And let's see, like, for example, one of the properties is A plus B equals B plus A. Well, A and B are the same size matrices. So A and B are same size. Otherwise, it wouldn't make sense. But they're the same size matrix. So that the order doesn't matter. And if we wanted to prove that, which these are the first proofs that are fairly straightforward, if we wanted to prove, to show that this was true for all matrices of all sizes, to prove A plus B equals B plus A. Well, these are consequences just of the definitions of equality in A plus B. So the first thing you'd have to do to prove this is names. You'd say, let A equals the matrix of entries Aij, and you say let for I equals 1 to M and J equals 1 to N. You say let A and B be M by N matrices where A is the matrix Aij and B equals the matrix with entries Bij. And then you'd say, well, consider the sum, you consider the sum A plus B. So the entries of A plus B equal, well, it's the entries of a sum. Well, they equal Aij plus Bij. That equality is due to the definition of sum. But then these are just numbers, so they're equal to Bij plus Aij. Well, this equality is just the commutative or order switching property of numbers. So this property here of numbers is why this thing holds true. And now we use we can say here, well, this sum are just the entries of B plus Aij according to the definition of the matrix sum. And then if we say, well, what this chain of equalities means is that A plus B Ij equals B plus A Ij. You can see that the far left-hand side equals the far right-hand side. And this, according to the definition of matrix equality, means that A plus B equals B plus A. And you're done. So the idea, the strategy of all the proofs of all of these 7 properties here that we'll look at in a second, the properties, not necessarily the proofs, are that you give names to the items and matrices involved in terms of entries, reduce the property to a property of numbers, then translate back from entries back to matrices. And I've written out, for example, here's the proof written out, which I just went over here verbally. I just went here verbally. Here it is written out with more care. Let A equal the matrix of entries Aij and B equal the matrix of entries Bij be any two M by N matrices. So I've given names and said that they're arbitrary M by N matrices, and M by N are arbitrary. So this covers everything. Their sum, A plus B, has the entries A plus Bij defined by, for all valid entries I and J. This is the equation that we put down here. The second equality follows from the commutativity, the order switching property of real numbers. The last equality from a second appeal to the entries of the sum, we sort of read backwards, of Bij, which shows this is equal, and from the definition of matrix equality is the claim A plus B equals B plus A. So this stuff just tells you why this is true in terms of the definitions and in terms of commutativity. And that's true. You can see this second property here. If you wanted to prove the second, you do the same thing. You give names to A, B, and C, and then you'd have to use the definition of addition twice, and you'd get this as like Aij plus parentheses Bij plus Cij. Then you'd use the associativity of real numbers to get it into this form and then translate back to matrices. Then these two are involved with the products, of matrices with how a sum of matrices interacts with a rescaling, and how a matrix interacts with a sum of numbers. And here's associativity of numbers. So each of these is just a sort of a wholesale representation of a property of arithmetic. Now this one's a little different. Number 6, it says for each pair Mn of positive integers, there's a unique M by N dimensional matrix Z, such that for any same size matrix M, M plus Z equals M. It's the matrix that acts like 0. That's why it's called Z. Now, it also says it's unique. Well, I give you another one of these proofs, but there's a third example. I go through and show you how you would prove that M plus Z equals M. Okay, well, I'm not going to go through this first one. You want to read over this. It's just like the last one. You're choosing the matrix Z as the matrix where all the entries are 0, right? So you choose the matrix Z, so all the entries are 0. Then you can show that the entries of M plus Z, M plus Zij equals M Ij plus Cij, but all the Zij is 0, which equals this matrix here, so you get this identity. What I wanted to emphasize was look at the second half here, but this is unique. Okay, because you prove something is unique. What does it mean to say it's unique? That means there can't be two of them. So what you do is you suppose there are two of them and then show those two things are actually the same matrix. So that's always the way you prove that something's unique. That's the strategy, is you assume there's two and show they're the same. So suppose that W is another M by N matrix with this same property, that for any M by N matrix Q, Q plus W equals Q. See here, Z is M plus Z equals M. Here, Q is any matrix plus W equals Q. Well, what you do is, we're going to apply this second one, Q plus W, where Q is Z, to say Z plus W equals Z. Then, because this has to apply to all matrices, it has to apply to W. So we have to have W plus Z equals W. Well, that's W plus Z equals W. So turn this around, we have W equals W plus Z. But this is just the order, right? We can flip that to Z plus W, then choose this one, then use this identity here, which just comes from this W here, Z plus W equals Z. And you can see, well, I have W on the left and Z on the right. So W equals Z, they're really the same matrix. They're just different names for the same matrix. So I can't have two matrices of a different form. So these are all things, the problem with these is that you sort of like think they're obvious, or they seem intuitively clear that they might be true in some way, or it seems like, well, why do you want to know this? And that's because we're going to play a game where you need to know that things are true. And these are your basic properties of matrix algebra. Then there's also the seventh one, which is a little bit like this one, which is for each n by n matrix M, there's a unique same size matrix N such that N plus N equals Z, the zero matrix. This goes back that there's always, if a number 5, there's a number minus 5, and 5 plus 5 equals 0. Just the analog of that. And you can see that this N is just going to be, here's a proof of that, is just going to be, this minus M is just going to be minus, it's just going to have the entries that are the negative. So the additive inverse, if M equals 1, 2, 3, 4, then dash M equals minus 1, minus 2, minus 3, minus 4, because you can see if I add M plus minus M, that's just going to equal the 4 by 4 matrix 1 plus minus 1 is 0, 2 plus minus 2 is 0, 3 plus minus 3 is 0, and 4 plus minus 4 is 0, and that equals Z. Okay, and you can prove that that's unique, that there's no other matrix that can do this, and that's what's shown up here, that if you have two of these matrices, N and Q, that they're really the same matrix. So there's only going to be one inverse. Okay, but this is sort of analogous to something that you may think is obvious or didn't need proof, like that minus 5 equals minus 1 times 5 as numbers. So this requires a little proof. If you actually started from some properties of numbers, you may treat this minus 1 as if you may treat this minus sign as if it's equal to a minus 1, because just you're so familiar with it that you just automatically do this and not without realizing it actually requires some kind of proof. And here's the analogous thing. If we wanted to prove this, what do? Is I form a sum here like this. I want to prove, see, this is saying that these, we want to prove that this form here is one version of minus M. And if we can show this is true, that these are the same matrix, we know that this is unique, so this is going to be it. It's always going to be true. So consider the sum of M plus minus 1 times M. Well, we'd like to sort of put a 1 in here, and then, because then we can use the distributive property of matrices over numbers to pull the M out and get 1 plus 1 is a 0, and then 0 times M is Z. So we're going to form M plus this number equals 0, equals the 0 matrix. Well, what can I do here? Well, I have to show that 1 times M just has they're the same matrix, M and 1 times M. Because when I can do that, then I can factor out the M. That's one of my properties of 1 plus minus 1. Then 1 plus minus 1 is 0, and 0 times a matrix is going to equal the 0 matrix, because this is going to multiply every entry. So then you see this equals 0, but the inverse is unique, so the matrix M plus minus M plus this thing is going to equal 0. So therefore, this is the additive inverse. Okay, so these are all like going back and looking at why things are true in terms of baby steps. And they're an exercise in precise thinking, or saying, okay, this thing, you can show that it's absolutely true. There's no logical way that it could be anything different could be true. Okay. So these are little proofs that enable you to practice the spirit of thinking. It's a little bit different than before. Now, okay, so let me stop there and ask you for